All right, Brian, got it. Okay, very good. Thank you again. Just a couple of prefaces before we get started. The first is we're here in Reno right now. We're in the midst of kind of a big windstorm, and it's not uncommon in the middle of these big windstorms for the power company to turn the power off preemptively because of the potential for arcing power lines and fires, if you all have heard of in the past. So if for some reason we lose connection, Brian has my cell phone, and we can at least try to do something that way. The second is I'm in the middle of fighting a pretty nasty head cold, so I have my cough syrup right here in case I start coughing too much, and I do apologize for that. But I guess there are some advantages to doing a Zoom presentation. So with that, let's begin. I do want to thank Brian for organizing this, and the Prairie Research Group for inviting me to come and speak. Some of you may have heard a little bit of some of what I'm going to talk to you about today because I was at Champaign-Urbana probably 4 or 5 years ago. So did a little bit of some of the things we're going to talk about today. But the idea was to talk about environmental sensing and the sensor revolution that actually is upon us. I think when I've given something like this talk before a few years ago, and I was saying the revolution is coming. Well, the revolution is here. So I think in the words of, I think that was Abby Hoffman might have said that. All right, let's see, where are we? Why are we not returning? Why are we not moving forward? There we go. All right. So what's led to this sensor revolution for environmental sensing? One of the big things is our advances in batteries, essentially the drive for small, high-density power sources for our phones or for our tablets, and now for vehicles and others, really has made remote sensing of developing sensors in the world, out in the world, much easier for us, and we can keep things running much longer. There are obviously serious environmental downsides to some of the battery development, and I might encourage all of you to read a book called Cobalt Red, which I just finished, and talks about the world cobalt market and what its impacts are on the environment. And cobalt is used in most LiPo batteries. We made significant advances in micro-electro-mechanical devices, so the little tiny things that move things around, and then of course processors. And those advances have been driven primarily by, again, cell phone technology as well as video gaming in many cases. The other thing that I think has really improved our ability to develop sensing capabilities and innovations has come about just in the last few years, where we really have much easier access to transfer technology between each other on sensors and on design and on instrumentation. COVID, to some degree, helped that in that we communicated much more across time zones in a much easier way, and learn to work together remotely. So things like GitHub, where some of the things I'm going to talk about today, the complete designs are available on GitHub. And then finally, AI and machine learning is revolutionizing how we incorporate that sensor data. And sensor data is now perhaps at times more important than our models of how the world works, at least if you believe all the AI folks. And again, how did we get to AI? There have been some fundamental advances in theory of artificial intelligence, but really the main drivers have been advances in hardware, and that's primarily the development of graphical processor units. And that's, again, thanks to video gamers in a large way. So if you're a video gamer, you have my respect. Thank you. That might surprise you, but that I said that, but you're doing okay. And let me bring a pointer in here while I'm thinking of it. Very good. Okay. All right. So let's see there we go. So today I'm just going to try to keep it fairly quick. If you have questions, I think it probably might be easier to save them toward the end. That might make it easier on a video presentation. We'll talk about fiber optic sensing, of course, because that's what we've been doing. My group's been doing for a long time, and I can't give a presentation without talking about optical sensing. We'll talk about unmanned aircraft or uncrewed aircraft, drones, essentially, and how those have now come along pretty far, and some opportunities for the future, I think, that will really change what we can do. Some of you may be using them already. We'll talk about the socialist revolution in instrumentation development, and that's again, kind of thinking about community resources. And then one thing I'll spend quite a bit of time on at the end is to help point all of you in the directions of where can you get some of this instrumentation? How can you actually use it in your own research? And that's the focus will be on the National Science Foundation instrument facilities, which there are a lot of, and many people in our world of environmental monitoring and environmental science don't know that those resources are available. So I'll help sort of direct you to those, and then obviously any questions. So we'll start out with distributed temperature sensing, which is fiber optic based. It is the measurement of temperature using only the properties of the optical fiber itself to change its optical properties. The fiber optic serves as a thermometer, and a laser is the illumination source or the energy source for it. And what's been revolutionary is that we can now make measures of temperature on an optical fiber every 25 centimeters, even less than that, 10 centimeters, even down to millimeter scale right now. So every place along the fiber, we can instantaneously get a measurement of its temperature. And we can do that for very long runs of optical fiber, 30 to 50 kilometers. So we get a huge amount of temperature measurements over a very short time scale. And we can resolve those temperatures quite well down to 10s to 20s millikelvin, which is quite resolvable. Not as good as say some of your thermistors that you might purchase, high quality ones, but getting close. What are the advantages? Let me click this out of the way. Fiber optic cables are quite inexpensive. We use them all the time. We basically use the same materials and the same fibers that the telecommunication industry uses. And so as a result, the cost for us is quite low. Once we put something out in the field, we're not going back out and disturbing things. Typically, in my world of working in the subsurface and hydrogeology, we would often do geophysical logging in a borehole, and we'd have to run a tool up and down through that borehole, through the water column or through the oil and gas column. And that disturbs what we're trying to measure. The advantage too is we can get very high spatial resolution because we can, and very high temporal resolution. We can cover large areas with optical fiber to get a picture of the temperature all around. And again, the idea is that optical fiber will come to some equilibrium with its environment. So we're measuring the environmental temperatures. And I would, at this point, give a shout out to Yufeng Lin, who's in your group. I think he's in the Illinois Water Survey, has extensive experience working with distributed temperature sensing, has a few instruments himself, and his group has done some really nice things. So if at the end of this talk you are seriously interested in using some of this, go talk to him first, and then after that, come and talk to us. Why won't you move? There we go. All right, so very basically, how does distributed temperature sensing work? We shoot a pulse of laser light down an optical fiber, and we look at the backscattered light, that is the reflected light that comes back as that light moves through the optical fiber. There's a little bit of scattering or interactions between the light photons moving down the fiber and the glass itself, usually imperfections or differences, slight differences in the refractive index in the glass. And that produces photons that then come back to our sensor. And we can estimate then the temperature of the fiber by looking at the backscattered photons that come back, not at the incident wavelength of light that we shoot down, but at what are called the Stokes and anti-Stokes Raman frequencies, which are slightly shifted from the wavelength of light that we send down the fiber. So if I send down, if you think of it, let's say I send down a green light down the optical fiber here, and I'm going to get most of that is going to keep going to the end of the fiber. I'm going to get some backscattered light that will be shifted to the blue side of the green, and some that will be shifted to the red side, so lower frequency. And basically, the ratio of these photons coming back we can use to calculate a temperature. The hotter the fiber, the more blue shifted photons, if you will, that return and we get back. The hotter the fiber, the more of those are produced. That tells us what the fiber temperature is. So essentially, it's inelastic LiDAR. So these are, instead of bouncing a signal off and waiting for the return, of the same frequency. We bounce the signal down, it bounces around in the optical fiber and sends back light in several frequencies, including backscattered light at the Rayleigh scattering. And we're going to use that later for acoustic sensing. So, okay, and just to give you a sense of the scale of what an optical fiber looks like, this is a fiber optic cable. So it's got plastic, it's got stainless steel braided wire over it. It has a capillary tube, a steel capillary tube in the center. All of this is for protection, both strain and abrasion. Excuse me. And then the optical fiber, there's actually two fibers here. It's pretty hard to see them. And these are about 250 microns at this point. They have plastic over them. But an optical fiber, when we strip off the outer plastic coating, is about the diameter of a human hair. So tiny, tiny. And as a result, the positive side of having something very small is that its thermal equilibrium time, the time to reach equilibrium with its environment, is fairly short. So it can be quite responsive. The bigger the steel cable, the bigger the armoring around it, the slower the thermal response is. So thinking about where you could use this, typically in environments where the temperatures are changing relatively slowly with time. And I say relatively, on the order of minutes to 10 minutes kinds of scales. Okay, good. So how does this scattering work? Well, here's a cross-section of an optical fiber. We have in the center of the optical fiber, we have this core glass. This has a higher refractive index. And then on the outside of that, wrapped around it, if you will, is a glass called the cladding glass, and that has a lower refractive index. So I shine some coherent light down the optical fiber. This is how we communicate as well. We're sending in information down. That fiber, excuse me, that photon may interact at a scattering site. And if it does, it will then, the photon will be absorbed by the glass, by the silicon dioxide, and then kicked back out as a photon. And if it's kicked out in this direction, we never see it again. If it's kicked out at a steep angle, thinking of photons as particles in this case, it's much easier for me to think of them that way. It's going to hit this refractive index contrast and get bumped out of the optical fiber, and we'll never see that. But occasionally, a scattering event will occur such that a photon will come back at a modest angle and be internally refracted in the optical fiber, in the core, and make its way then back upstream to the sensor. And we're going to measure the energetics, the wavelengths of those photons returning. Okay, so that's how distributed sensing in optical fibers typically works, is we're looking at that backscattered light. Remember, light doesn't interfere with itself, so even though we're sending down a milliwatt of coherent light down this way, I can be sending back 10 to the minus 5 milliwatts of photons back upstream, and never the twain shall meet. So we don't have any interference. So this is, again, a typical optical fiber. It's got a core glass in the center of high refractive index, cladding glass of low refractive index to keep the light inside the core, and then things on the outside to make it stronger. Okay. All right. So let me give you some just kind of a cool example of where we are using this in remote environments to get you all thinking of maybe where you could use it particularly in lacustrine environments, lakes, streams, rivers, things like that, is where fiber optic distributed temperature sensing gives you incredible windows into the processes that are going on in water bodies. So we're going to go down to Antarctica very briefly and talk about the Thwaites Glacier, and we're going to look at a mooring site. This is, you can see, life is a little challenging to work down there. This is about 7 hours by plane from McMurdo Station down in Antarctica. The winds are a little tough there. You can see this mooring tower has been bent over by the wind. Okay. All right. So where are we going to go? So Antarctica, this is Antarctica here. We call an East Antarctica and West Antarctica. Sometimes that's a little challenging to understand which is which, but think of West Antarctica as anything west of London, England, or Greenwich, if you will, 0 degrees latitude over to 180. And then from the longitude, sorry, and then longitude 180 back to 360 is the east side. So shown here are the major ice sheets of Antarctica, the East Antarctic ice sheet, this here, and the West Antarctic ice sheet here. On the outside of these, this is sea ice, and this is the typical extent of sea ice formation in the winter in Antarctica. But if I take all the ice away from Antarctica, I get a very different picture of what the continent looks like. The eastern part of Antarctica, most of it would look like a continental landmass. There are some areas that would be submerged under the ocean, but for the most part, it's above land surface. West Antarctica, in contrast, is primarily a few islands out here on the coast, corresponding to out here, and then an enormous trough in the ocean of about 2 kilometers depth. Here in West Antarctica. So the ice that lives in East Antarctica is essentially living on land, not unlike the big Laurentian ice sheets that came down across Canada into the northern parts of the world where you guys are. But on the western side, this ice is actually grounded below sea level. And this is the major concern for warming climates, and that oh, excuse me, I do apologize. That under warming climate and warming ocean waters, that this ice will become melted from below, and this entire ice mass in West Antarctica could indeed collapse into the ocean. The ice that is below sea level, of course, doesn't raise sea level whatsoever. It's below the ocean, it's already floating. However, the ice that is above sea level, excuse me 1 second. I do apologize. The ice that is above sea level, of course, that will raise sea level, and it has the potential, if we melted this entire ice sheet on the west side, to raise sea level about 3 meters. And hence it's been called or nicknamed the Doomsday Glacier. We're going to be showing you some data from out here right at the edge on the major outlet glaciers. Most of this ice is making its way out toward the ocean in this direction. Some also is going out this way, but most is heading this way. And so we'll be studying what's going on at these outlet glaciers. And this is what the world looks like as we are out at the ocean. We have ice which is grounded below sea level. That's the ice I was showing you that's in West Antarctica, the ice sheet. And then as that comes out toward the ocean, eventually the ice detaches from its bed and becomes an ice shelf, a floating ice shelf, and that moves its way out toward the ocean and eventually calves off, producing what you see are the large tabular icebergs. How that process is melting is we're bringing warm water, roughly 2 to 3 degrees centigrade water, from the deep oceans. It comes up over the continental shelf. And then because the continental shelf slopes backward or downward, that warm water can make its way all the way back to the grounding line, the area where the ice is actually still on the ground, and melt here. And as this melts, the grounding line begins to recede, and the speed at which the ice moves from left to right is a function of its ice thickness. So as we degrade and erode the base of the ice, we are exposing a thicker and thicker ice mass to this floating boundary condition. And in that case, the ice begins to speed up. And so the thought is that this could be a runaway process, as once it begins, the ice moves out faster. We now see more melting, moves faster, and off to the races, and it's all gone. And this has happened at least multiple times through the last million years of several glacial cycles. We know that from coring data. So what have we done? We've drilled holes through this ice shelf and have installed moorings to understand what's going on in the ocean beneath, as well as what's going on in the ice shelf itself. These moorings contain distributed temperature sensing systems, distributed acoustic sensing. We're going to talk about those in just a little bit, as well as a standard set suite of oceanographic monitoring tools, such as temperature, conductivity, temperature, salinity, pressure, current, and other things as that. And just to give you a sense then of what data look like from an optical fiber drilled through the ice into the ocean below and then frozen in over about a 1.5 year period. This is a temperature profile or a series of temperature profiles, time slices from the system was installed in January of 2020 and actually continued to run to January 2023, just showing you some beginning profiles through the ice. The temperatures are getting colder as time progresses, and that's because we had to melt our way through the ice, and the ice has refreezing, and the temperatures in the ice then are slowly equilibrating back to pre-drilling conditions. And so our coldest temperatures here is about minus 19 degrees C. And then as we come down and we hit the ocean, we have a really steep profile in temperature and then down into the ocean. And you can see even in the ocean, we see fairly uniform temperatures well above freezing down at the bottom of the ice shelf, the bottom of the ocean beneath the ice shelf. This is this circumpolar deep water, which is quite warm and salty. Actually, its source was up in Greenland. And then you can also see fluctuations in temperature here over time in the water that is close to the ice. And this is what we're most interested in. So here you see now changing that plot again a little bit. Now the bottom axis is time, the left-hand axis is depth. The ice-ocean interface, the bottom of the ice is right here. And the colors represent temperature, and the contours represent temperature contours ranging from minus 1.5 up to +1. And this is about 6 million data points of temperature in the ocean in the water column. The white lines are times where we had data gaps. Through the winter, the system stopped working, ran out of electricity. But what you can see is you can see a lot of fluctuation in temperatures near the ice shelf, close to the ice shelf in one season. And yet the next season, same time, so February, March, very little fluctuations. So much different conditions underneath the ice than from one season, in this case, 2021 to 2021-22. And then you can also see, where'd it go? There we go. You can also see coherent structure in the deep waters. So definitely a warming event here, of warm water coming in under that shelf and dropping these contours and pushing them up here. So a tremendous amount of information. We are still processing all these data, but we have some pretty good stories as to what's causing this. Part of the change in the near surface conditions, where you went from lots of fluctuations here to steady conditions here, as a result of whether there is sea ice out in front of the sensors. So this is, our sensors are over here on the Thwaites East ice shelf. And there's a big open embayment called the Pine Island Gyre that in 2020 was open, ice-free. The next season, that ice never left. And so what we're seeing underneath the ice shelf is the effects of winds and surface currents driving fluids underneath the ice shelf. Whereas the next season, when there was sea ice formed and didn't thaw out, we don't see those kinds of fluctuations. So really important dynamics as to what's controlling the flows underneath these glaciers, these ice shelves, and what's important with respect to melting. Okay, so that's just one example. Again, think about where you might be able to use distributed temperature sensing in your work. We've done a lot. Our group has supported quite a few projects in the Midwest, particularly looking at things like stream habitats, river restoration projects, fisheries management to manage temperatures for certain aquatic species or endangered species, redesigning channels, and really getting then a sense of what did the river restoration do with respect to temperature, particularly in the summertime, usually when it's the more serious times. Okay, so I don't know if I can do this, but I'll try, admit whoever that was. Distributed acoustic sensing. So this is something that's come along in the last few years. And this is a game changer, and I think will be a game changer for many of the things that we do in the environment. Even though right now the folks who are really taking the lead on this is the seismology community. But there's lots we can do. So acoustic sensing is basically measuring the strain rate on an optical fiber. And now we only use Rayleigh backscatter. We send a pulse of light down an optical fiber, and some of that Rayleigh light is backscattered, and we calculate when the timing, when did that come back? And then we take another laser pulse, a microsecond later or even shorter, and we see, has the distance to that scattering site changed? So we're basically looking at movement of scattering sites along an optical fiber. And you would think, well, an optical fiber is not going to really move. But if I send a P wave, a seismic wave down an optical fiber, and I don't know if you can see here's the fiber, it's the P wave, moves down through that fiber. What's it going to do? It's going to compress the fiber as it's passing, and then it's going to expand the fiber as it goes past. Now, tiny amounts of strain, but we can measure that with this technique. We use standard, what's called single mode fiber, which is the standard fiber that's buried every place for telecommunications. And we are capable of measuring picostrain. And picostrain is the equivalent of 1 meter of change in distance between Jupiter and the sun. I'll say that again. So we can measure a 1 meter change between here and, well, not even here, from the sun to Jupiter with this technique. So it's incredibly sensitive. And the cool thing is, too, we can measure at very high frequencies in the kilohertz range. So that's even above the acoustic side, above what we can hear. But we can also measure strain at very slow strain rates. It's not as easy, but it can be done. Things like earth tides and reservoir loadings, let's say, even over maybe a month period. We will be able to detect those kinds of changes, those strains, with this technique. Okay, where are we? There we go. All right, so just kind of how it works. I send an optical pulse down to get a backscattered pulse off of, again, some kind of a slight flaw in the glass itself or a slight difference in the refractive index of the core. And that backscattered pulse comes back and I time it and I measure it. So I get, let's say, the blue line here. So this is as a function of distance down the fiber. This is how many photons I might be seeing down the fiber. Follow the blue line. Okay. If I come back and do that a second later, just to give us enough time, if indeed that fiber has strained, has actually changed its length slightly, then this backscatter amplitude versus distance is going to be shifted. Not going to be shifted everywhere. It's only going to be shifted in the places that the fiber actually strained. And so what we do is we calculate then the phase shift all the way along the optical fiber from 1 second to the next, or in this case, microsecond to another microsecond. And that then gives us a measure of the strain rate. How much has the fiber moved in a fixed amount of time? Right? We can get that back to strain if we want to, also pure strain by just knowing how long we were integrating that process over. Okay. All right. So just to give you a sense of what can we see with this. So for most of us, I'm not sure if there's many seismologists in the group that are there. Seismologists love this. This is the greatest thing since sliced bread because they can now measure. They can turn an optical fiber into thousands of seismometers. Okay? And so I'll just show you some data that are sort of geophysical data to start with, and then maybe get you thinking about where else could we use this. This is a fiber that actually is one of the fibers that's frozen into that ice shelf that I talked to you about earlier. The bottom axis is time. The left axis is distance or depth, if you will, downward. And at the surface, we shoot off, in this case, somebody with a sledgehammer onto a steel plate onto the snow. And what happens is that P wave then propagates down through the ice, and we're measuring it in the distributed acoustic sensing. That's this bright green line. Okay, this is the speed of a P wave propagation. You can see there's a slight change in the velocity here. It's kind of fast here, and then it slows down. There are some rheologic changes in the ice. Then we get a bounce back. Okay, that's the ice-ocean interface because there's a change in density at that point. So we bounce some of this P wave acoustic energy back. And then we continue that P wave propagating downward through the ocean. Now, it turns out we originally thought, this is great. Look at this, beautiful information. Nice coherent signal all the way down. So we're seeing that P wave propagate, which is something of a function of the density, the salinity and the temperature of the water. Unfortunately, this speed and the ice are about the same. And the acoustic velocity in water is quite a bit slower than it is in ice. So what's going on here? It turns out in this case, and we've seen this in a few other cases of fiber that's hanging, is that the P wave is actually moving through the steel casing that is the fiber is encased in. So we're actually, and it's a little hard to imagine, but the energetics are actually just moving its way down the cable. So the ocean, if we could listen out to the ocean, it would be out here, but this is actually in the cable. Okay. Now, what's more interesting for all of us who are perhaps not interested in ice and glaciers is, can we use distributed acoustic sensing to tell us something about the near surface geology? In particular, one of the big areas of interest out here in the Western United States is understanding the likelihood of earthquake shaking, the shake intensity at various locations in the environment. An earthquake, intensity, a magnitude 7 earthquake is going to shake some parts of communities much more than others, depending upon typically the shallow subsurface and something that's referred to as the VS, which is the shear wave velocity, VS 30, the shear wave velocity at 30 feet below surface. So what we've done here is we said, well, we could string an optical fiber out on the land surface and put some seismic noise into it and use it just like you would a traditional geophysics survey. Or we can make use of a telecommunications fiber that's already buried in the out there, and hook our instrument up to the telecom fiber and listen to it. So the fiber is buried, standard telecommunications cable is not being used. And this is called dark fiber monitoring. And this has been extensively used now in the last few years. It's shown to have some relation. We can see effects of water table changes on the shear wave velocities using this technique. So it's really powerful. And this graph is just, again, distance. No, sorry, this is time on the bottom axis. No, sorry, time on the left-hand axis, distance along the fiber here. And what you can see, these straight lines, this is a car driving along above the fiber and going at a constant velocity and setting off the fiber as the car rolls. So that's the only seismic signal, or it's only seismic input we needed. And we were fortunate to be monitoring. What happened here is this is a magnitude 3.4 earthquake that occurred at this time. And what do we see is we see at all time, and I think I have this axis. I'm apologize. This is time on the bottom axis. This is distance over here. I'm sorry, I have it wrong. Anyway, this magnitude 3.4 earthquake occurred quite some distance away. And as the P wave impacted this fiber, because it's a spherical wave, but we're a long way from the source, that P wave looks like a flat wave, and it hits the fiber all at the same time and strains the fiber everywhere at the same time. So again, we can use it now for earthquake monitoring. This is going to revolutionize our seismic, our early warning systems for ground motion. We will be using dark fibers everywhere. But thinking about what you all could do with this, we have lots of dark fiber buried around the built environment and even the not built environment. And one can use existing fiber to start looking at the physical properties of the sediment down probably 30 to 50 meters. Once you get down below that, the acoustic input from typical cars and things like that is not enough. But if you're close to a train, that produces a great signal. So think about sort of the geophysical modeling, monitoring the subsurface. Okay, so and here we are. We're actually in the telecom switching room, and we've just connected up to a standard telecom. And again, we're sorry we slowed down your YouTube presentations or uploads while we were stealing some fiber. So distributed acoustic sensing, it's a game changer for seismology, for shallow hydrogeophysics. The instruments are indeed expensive. They're up to a couple $100,000, but the fiber out there is free. It's very data intensive, produces terabytes per day, potentially. But the good news is, on the cost, is these instruments are now available to you in the community. And we have several interrogators, or the boxes that do the work, spread around a couple of different instrument centers, which we're going to talk about in a little bit. If you are interested in this, we are just wrapping up a distributed acoustic sensing research coordinating network. But that network has amazing resources currently held on the EarthScope website or the IRIS website. Introductions, great tutorials on how this works. I just gave you a quick intro on how it works. And brilliant examples of using this in hydrology environments, in geomorphology environments. Okay, so next area of sensing that our group is working on is a group called OPENS, and this is a component of our instrument center, CTEMS. And the goal with OPENS is to develop low-cost, rapid turnaround environmental sensors. So if you have an idea, I need to measure this, and I need it to be inexpensive, come and talk to us. It's a great student project opportunity. We love to have students involved with this. Just give you a couple of examples of some of the things that have been built out of this group. Very low-cost soil and meteorological sensors and data loggers. A relatively low-cost landslide detection system that includes acoustics as well as soil moisture. And again, just all been low-cost, off-the-shelf, put together. Dendrometers, things which actually measure the diameter of a plant stem, which is going to change daily with root water uptake, as well as growth over time. Super low cost and very, very high resolution to tell you things about the ecology and the water stress. And this group, we look for ideas that are transformational. So, what's a sensor that we don't really have working well? Or if we do, it's really expensive. It's got to be feasible, obviously. It's helpful if it has some kinds of funding from the proposer, a sponsor. But the lab is open to proposals from students and faculty around the country. And the key thing is it has to be openly publishable, okay? So that we want to get this out. As I was saying earlier, part of the instrument revolution is this idea of instantaneous and easily accessible information on how to build sensors. And most everything that this lab does goes right up to GitHub. All right. So I'm going to start picking it up a little bit. I don't want to keep you guys past your time. A little bit about unmanned aircraft. This is another revolution that I think finally is getting beyond what I'll call the gee whiz factor. Look at that. Isn't that cool? To, what can we actually do with the information that we might gather from essentially drones, okay? So again, the most common thing that we've been using these drones for, I'm sure some of you have done this. If you haven't, you should be. It's really easy. Topographic analysis. So techniques called structure from motion, which is basically high performance photogrammetry, can give us topographic information and topographic information in low vegetation density environments. Airborne LiDAR on drones is now becoming much more common, and it actually is now finally starting to work. And that gives you the ability to look at topography in much more dense vegetated environments, and also to get some sense of the topography, the vegetation topography. And this topographic analysis, it's used extensively now for the national natural hazard evaluation and we see it now. You'll probably see this quite often. You'll see drones flying over construction sites all the time. People are doing this now. Construction companies are doing it to map kind of how the project is going, but also to do things like understand how much fill material is stored on site, or how much cut material how much has been cut. So again, just in real time, getting the topography of a subdivision. And I just want to show you a couple of examples. So this is a beautiful example of a stream, which is coming down across this kind of funny looking thing. And then all of a sudden the stream's been moved over to here. And of course, that's a very recent fault scarp. This scarp is only about 3 years old. And again, about a 10-meter offset on the stream itself. So amazing resolution. Just this probably took 30 minutes to fly over. This is just from photogrammetry to give you a sense of the topography and what's been going on in this stream environment. Again, fairly low vegetation density, so this makes it fairly easy. This is some data from Praveen's group. This was the CZO in Iowa, a cornfield, and Praveen invited us out there. Thanks, Praveen, a couple of years ago, to do some flying to look for tile drains. I'll show you that just in a second. But we were flying over this cornfield, which is fallow at this time. You can see I've just blown this picture up. You can see the furrows. And then what you also can see is this really subtle drainage coming through this field, which I think is on the order of about 2 centimeters in depth. So it's really, really, you know, I think imperceptible by the folks on the ground. These are the tire tracks you can see here. So some pretty amazing topographic relief can be quickly gathered from drone aircraft flying over. We also can do things with not just with photography, but we can look at multispectral imagery. Typically, NDVI is a really common tool that we can fly on drones very, very easily. Give you a sense of vegetation health. This is some work in Colorado at the East River experimental site that Berkeley Labs is running. And this is the topography. You can see the stream meandering all over the place. This is the NDVI image of that same area. Very dry conditions outside the riparian zone. But we were able to gather some information about hyporheic exchange at this site by looking at vegetation density between through the big meanders in the creek. And the most important thing we actually got out of this was getting the topographic relief of the river channel itself. We were able to reconstruct the gradient of this creek and stream, about 100 CFS stream, all the way down just by flying over with photographic information. And so really important with respect to, you know, what is the gradient of this river? And this is about, I think, centimeter by centimeter measurements of topography of the stream itself to give us the gradient. Moving on, we can do thermal imagery. This thermal imagery is really quite useful. These are actually, this is again at one of Dr. Kumar's sites. You can see these white dots going across. This is somebody's footprints, which are showing up in the thermal imagery extremely well. So our hope was in this site, we were hoping to measure, to resolve where the tile drains were underneath this field. And indeed, we couldn't with the thermal imagery. And we just had to use the regular RGB imagery. And the tile drains showed up really nicely by this, what the terminology is called chalking. So above the tile drains, as I recall, typically the soil moisture is going to be a tiny bit lower above the tile drains because the water table is there obviously deeper. And you end up with these slightly whiter zones with a little bit of image processing. And you can see some other tile drains all in through here. So pretty simple technology. Again, just very inexpensive and fast to do this kind of work. We can also do other things. We can do airborne magnetometers now with drones. And again, why do we care? Why is this better than anything else? Well, I could walk the landscape with a magnetometer, but I can't cover a lot of landscape. Or I can fly it with a helicopter or aircraft, but I've got to do that from a fairly high elevation. So now I don't get much spatial resolution. And the drones kind of fill that gap in between. I can get quite high spatial resolution because I can fly low and slowly. And I don't think we need to see the video. There's not much happening. Okay, but I want to close now with something that is hopefully of value to all of your use is how do you get access? You as researchers, as scientists, students, how can you get some of these instruments? Because many of them are expensive, and many of them take a pretty significant amount of time to get yourself trained up to be able to know how to use things. And so why not use the resources that are out there? And that's what my group gets paid for, as well as a few others I'm going to show you, is our jobs from the National Science Foundation is to provide you with resources and training. We've spent millions of dollars, NSF, in earth sciences alone, far more in some of the other disciplines. These instruments and certainly workshops and things, they're open to all. There are usually some limits with respect to for-profit or not-for-profit agent groups. So if it's for-profit, again, you can talk to them if you want. The training is extensive. They have all of them have, including us, I think, just to brag a little bit. We have great workshops and great training on how to use this stuff, and we provide resources to help you guide in your experiments. The other nifty thing for those of you who are students or early career faculty, many of the instrument facilities have essentially a no-cost option for you. Maybe you might have to pay shipping for the instruments, but other than that, it can be free. It takes maybe a little proposal or something like that. So what are some of these facilities that we have in the earth sciences? And I've just listed them here and kind of what they do. So again, EarthScope is seismic and terrestrial laser scanning, as well as geodetics. Near Rapid does natural hazards response really quick. If there's a flood someplace, you call them up and they will suit you up with everything you might need to measure debris flow volumes or contaminant concentrations, things like that. NCOM is the Airborne Laser Mapping Group out of the University of Houston. Does beautiful work for LiDAR mapping. Open Topography is not so much instruments, but more tools on how to process LiDAR and structure from motion topography. And then they're a great data repository. Then the group at Austin is large seismic analysis. And the one I want to show, actually, let me go one more. Yeah, so I don't forget, this was meant to remind me. I put in the chat the links to all of those organizations, as well as a couple others I've mentioned. And so please feel free, if that's not in the link, I'm sorry, in the chat. Let me just double check that it is there. Lost the chat, where'd it go? Yes, it's there. Okay, good. So let's go back up. So one place that we've just launched, and this is literally just a month or two ago, is all of the instrument centers I showed you above have some unmanned aircraft or drone capacity. NSF never quite, let's see, are there any NSF program officers listening? Good, none. Okay. So NSF never quite got its act together with respect to drones because the rules were changing so fast out in the world. And so each of the instrument centers ended up with little bits and pieces of unmanned aircraft to support bits and pieces of research. Poorly, on our side, probably poorly advertised and poorly integrated. So what we decided to do was to form a federation in the Soviet socialist style that most of us apparently were. And we now have a UAS federation. And this is the website. We have 35 aircraft. These are the remote sensing capacities that we have that are available to anybody who wants to use them. So pretty much everything that you might want from a remote sensing side. And we can provide aircraft, we can provide pilots, or if you're comfortable flying and you have all the required permits and operators licenses from the FAA, we will be able to offer you the aircraft at quite low costs. So the groups that are involved, it's NERI at the University of Washington, Open Topography, EarthScope, which is the old Iris Pascal and UNAVCO, which are now combined, so the geodetics and the seismic, NCOM, and our group at CTEMS, wherever we are, someplace over here. So I put the link to the website. We're still in development, but if you have unmanned aircraft needs, contact us. We also have a lot of training stuff that we're trying to put together as well to really optimize and just make it easier for folks to get access to this equipment. It's there. All right. So I think we're coming up on the top of the hour. So again, we've made transformative advances in measurement and data processing, and it's here. And I just think of self-driving cars as how the heck did we get to that? It's so amazing that I sit in a Tesla and I look and see on the screen that it's showing me people walking in front of me on the car. So yeah, sensing has come a long way in the last 20 years. Computation is coming right along. The Weather Service, all their reanalysis products, and then the Weather Service now is using a lot of machine learning for their forecasting going forward, particularly their mid and long range forecasting. It's been a little bit of a challenge for them, I think. It's a challenge for all of us to give up our process-based models for something that we may not quite understand. Fortunately, I think there is space for both to continue going forward. On that topic, while I have the audience, one thing that I have seen with respect to machine learning and AI is if you're reviewing proposals from the National Science Foundation and you don't see somebody trying to take whatever project they have and have a machine learning component to it, you'll be shocked, because pretty much every proposal will have some aspect of, yes, and then we will apply machine learning. And that's great. But I would just caution all of you who are writing proposals that my understanding of machine learning is limited, but I know enough to know that you need big training sets, big data training, large data sets to train with. And many of these proposals have very small data sets. And I think it's just playing around with numbers when you get to that point. That's a personal opinion, but just be careful if you're going to apply machine learning. Make sure you have the training data that you actually really need. And I would just say, because of machine learning, we are at another round of fundamental advances, and machine learning can't go forward without a lot of our sensing capacity. So with that, I just want to thank all my contributors. Again, listed here, most of this work is not mine. When you get to be my age, most of the work is done by everybody else. You just get to talk about it. But great teams that we've been able to work with, and I probably don't have everybody on here that we've worked with, but look forward to taking any of your questions. And I hope to see some of you sending instrument requests off to some of these instrument centers that I showed. So with that, thank you very much, and I will stop sharing.
Thank you. We have a very large group. So if you're online and you want to talk, please raise your hand. It will be bouncing back between people in the room as well as people online. David?
Yeah, hi. Yeah, we're very happy to use CTEMS for a project for atmospheric work a couple of years ago. I wanted to ask you, has there been any work on not only measuring temperature in the atmosphere, but pressure waves or gravity waves?
Pressure certainly in the atmosphere, or yeah. Not that I have seen. I have seen some. I mean, we certainly. Well, I take that back. Yeah, there's been some really nice work done on looking at wave propagation in using telecom cables that are on the seabed. You can actually really nicely see wave motion coming across. So but I haven't seen anything done terrestrially to look at, air pressure. So I don't see why not. Gravity waves, I don't know. That's should be. I mean, but I don't think
they're pressure waves in themselves. So
yeah.
Thank you.
Yeah.
We have a question online from Peg asking about the processing needed for UAV imagery.
Sorry, could you repeat that? I couldn't quite pick that up.
We have a question online from Peg asking about how much processing is needed on UAV imagery. Do you do processing or does the agency process it?
Yeah. So how much processing on the drone imagery? Certainly, structure from motion is you can do it on a small laptop with essentially free software. So it does take a little bit of training, but there's great training manuals out there from Open Topography. Very quick and easy. LiDAR data still requires a little bit more processing. That's not a trivial exercise. And I would point you to the folks at NCOM to help there. They will certainly help you if you had LiDAR data. But there are some freeware LiDAR processing packages that are out there. So it's not, I haven't done very much of that, so I can't speak to it too much. But structure from motion, it's trivial. I mean, structure from motion, again, this photogrammetry. How many of you have had crowns at the dentist, the sort of the same day crown thing? Okay. They're doing the same technology. That little thing they sort of wave around in your tooth, in the hole in your tooth, is basically taking images of the inside of your tooth, where the hole is, and then that is then processed at the dentist's office or maybe in the cloud to produce a 3D volume of the crown for your tooth, and then that's just plugged into a 3D printer, and off it goes. So it's easy. And great things for students to work on. Students love it. It's really fun.
Aaron Bauer has another question.
I was curious, with the drones, my understanding is that I have areas that are quite large, more than a mile, that are remote and forested and over streams, and the drones can only go a mile to a mile. Does that mean that so how are these drones that are offered to us? Are there other things that can go more than a mile, that can be doing like 5 square miles from a location?
Yeah, to do that, that does require some special permission from the FAA to basically be flying out of line of sight. But that is not that difficult today. It is becoming much more easy. The FAA has become I would say less uncomfortable with drones than they initially were. It's not trivial. I don't want to trivialize it. It's not easy. And a big area like 10 square miles, yeah, that's the point where you would begin to think certainly about using a fixed wing drone, because that's a big area. So when you do that, your spatial resolution is going to go down because things fly faster. But yeah, that might be getting sort of toward I'll say the more challenging acreage when you start getting in that size, because then you begin to border on, well, maybe we should just use a helicopter or something, but that's too expensive. So it can be done. It's just not as easy, unfortunately, but we can help you with that.
Online, we have a question from Praveen.
Hey, Scott. Thanks for taking the time. Wonderful talk. So I don't know, maybe about a decade ago, maybe you were at Guwahati at that time. I remember having some conversation with folks at Guwahati to develop or create a library of fixed-wing aircrafts. And my thought was probably some of the military drones were being decommissioned and could potentially be repurposed, and they could fly for long periods of time, cover large areas, and provide high resolution measurements of whatever we wanted, hyperspectral or LiDAR or some of those other things. Has there been any progress with those kind of concepts? I mean, what's your take on fixed-wing aircrafts, drones for long duration flights?
Yeah, there has been some energy put into it for work in the polar regions, and again, for safety wise, and just it's somewhat of a no man's land or no person's land. The USGS has made attempts to kind of go down that mid-size market for unmanned aircraft, and to be honest, I don't know where that stands today. They've Yeah, I don't have a good answer for that question. I know they have tried, and they've run into some, I think, funding issues on that. But it is certainly out there. The Canadians, John Pomeroy's group at Saskatchewan, has done that, and they have long duration flights over the Rockies, basically doing the equivalent of what the Airborne Snow Observatory is doing here in the Western United States with crewed aircraft. So yeah, it can be done. I don't think we certainly are not interested in going that scale. That's a whole nother budget issue. I don't think NSF is either. But I know the GS was thinking of it. And the Army Corps also, to some degree, they have some rather large aircraft that they're using. So that might be a place to look.
What is the speed of this fixed wing aircrafts? Like, we have lots of smaller aircraft companies that do, you know, crop dusting and laying seed and stuff. And can we utilize them to carry some of this instrumentation to do this fixed wing kind of logo over our areas? What do you think?
Yes, easily. And in fact, I know NCOM at Houston has developed a couple of like pod-based LiDARs. So it's basically something that can be bolted on to, and it's FAA approved, can be bolted onto the skids of a helicopter, or it can be bolted onto the struts on a Cessna, 212 or 182, something like sort of that size plane. Yes. And I would point you to NCOM to talk about that, because they have, and they also have hyperspectral imagers as well. I don't know if those are portable from one aircraft to the other yet.
Yeah, so I have flown on one of those NCOM flights, Scott, when they were here for the CCO project, and we pointed a thermal camera through their hole in the belly, and you could probably see some very dramatic illustrations of how the temperatures change across the landscape.
Yeah, I remember seeing the video.
Yeah, those are manned aircrafts, though.
Yeah. But yeah, if you have access to things like crop dusters and whatnot, why that would be, and in fact, maybe even dual purpose while they're dusting. There's no drama whatsoever, and maybe adding one more sensor on top of the aircraft. It's certainly possible.
Online, we have a question from Caitlin Bloomer. She's asking about difficulty getting permission to use private lands or government lands. She's looking at freshwater systems and using your DTS systems.
Yeah, that on private land, I would say that the best solution there that we've always found is it's a person to person kind of thing, explaining what you're trying to do to the landowners or the land managers, and getting their buy-in, and including them in the research in some way. Yeah, that's a person-to-person thing usually. On the federal side, obviously, things like you're not going to be able to fly aircraft in national parks. That's a no-go. It can be done. I know the USGS has done a tiny bit of it in Yellowstone, but it's probably took more time than they would ever do again. So you just have to sort of pick your poison in that case. But private landowners, we've found, generally speaking, are conducive to us doing things. One of the things with distributed temperature sensing, I would just warn you about, particularly working in aquatic environments, is you are putting out something that is a hazard to navigation, either to people or to boats in the water column, or on the bottom of a stream. So you'd have to pay a little attention. We've done some work in trophy trout streams, for example, where we made sure that the angling community in that area understood what we were trying to do and knew about the hazard, and also were more than happy then, once they understood what we were trying to do, to call us up and say, hey, half your cables is sitting on the bank halfway down the river with a log tied to it. Did you know that? I said, oh, thanks. Okay, we'll go fix it. So that's one area just to pay attention to if you're doing either DTS or DAS, that you are putting something long and tangleable out in the field. Oh, I see. Can we, Praveen just put something in? Oh, I'm sorry. I wasn't looking at the chat. How can we get beyond point scale water quality measurements? I don't know. That's a good one. We can do it with temperature. It's pretty hard. You know, it's pretty hard with chemistry.
We have another question here, David, again.
Yeah, most of our experience with community instrumentation facilities has been through NSF, but do you need an NSF grant to use these facilities at these various locations?
Great question. So the question is, do you need an NSF grant to access the instrumentation? And my answer to that is, it depends. But for the most part, no. One or two of the instrument centers, and particularly the ones that are housed surprisingly, out of the engineering side. So NERI, which is the Natural Hazards Environmental Research Institute, I think it's called. They often have requirements, and that's something that, whether NSF required it or they chose to do that it has to be an NSF project. Also, I would also say that the instrument centers work differently. For the way our instrument center works, if you have a project and you come to us and say, I need something, and we will say, sure, this is what it's going to cost you. You know, it's not very much, but it's going to cost you. Off you go. Some other instrument centers would say, well, when you are writing your proposal to do X, Y, Z, and you want a piece of equipment from us, you write that into your proposal, and then we, the instrument center, will tell NSF, yes, we can support that. So that's a little bit different business models between the instrument centers. But we're happy to, again, just contact them. They all have contact people that will explain to you exactly. But no, there's usually no requirement to be an NSF project. NSF projects typically may get priority, but from what I've seen, that doesn't make much difference in timing.
Questions in the room? Any more questions online?
Yeah. Were you on? Yeah. So I'm going to put back in the chat one more time this list of links so that you all have it. And maybe, Brian, you can email it to folks. Oh, I don't have it.
Everybody gets it.
Okay.
Well, Scott, thank you very much for presenting to us. I think it was very informative, and you've given us a lot of good things to think about, and maybe some resources that we can take advantage of. So, everyone, I'd like to thank them again. Let's give another round of applause for coming. The virtual one, that's my first time seeing lots of virtual hands like that before.
Scott, thanks a lot.
Thank you all. Thank you all for listening. I do apologize for my coughing in the middle. There was nothing I could do about that, but I do appreciate your patience.
You couldn't hear, I was joining you on this side.
And feel free to reach out again. Brian has my email. Feel free to contact me, even though I'm sort of partially retired. I still seem to get involved, and I'm happy to direct, if you have questions specifically, I'm happy to direct you to the right people in the other instrument centers. I've gotten to know them pretty well. And again, don't hesitate to contact me or them. We're all pretty open to this. It's surprising how open the community, the instrument community is to helping researchers. Okay, thank you all.
Thank you very much for everyone online. Our next talk will be in 2 weeks. And we'll be sending out a notice shortly with a bio and abstract also. Again, Scott, thank you very much, and good luck.
Thank you.
Bye-bye, everyone.